Welcome back to another lesson in our study of the transport layer of the TCP IP model based on the text by Jim Caros and Keith Ross, Computer Network and a Top-Down Approach. Let's discuss the issue of fairness in this lesson. Consider a collection of TCP connections, each with a different end-to-end path, but all passing through a bottleneck link with transmission rate of R for capacity bits per second. By bottleneck link, we mean that for each connection, all the other links along the connection's path are not congested and have abundant transmission capacity as compared with the transmission capacity of the bottleneck link. Suppose each connection is transferring a large file and there is no UDP traffic passing through the bottleneck link. A congestion control mechanism is said to be fair if the average transmission rate for each connection is approximately the capacity divided by the number of connections. That is, each connection gets an equal share of the link bandwidth. Is TCP's AIMD, additive increase, multiplicative decrease algorithm fair? Particularly given that different TCP connections may start at different times and therefore may have different window sizes at a given point in time. Let's consider the case of two TCP connections sharing a single link with a transmission rate R for capacity, as shown in this figure on your screen. Assume that the two connections have the same maximum segment size and round trip time so that they have the same congestion window size. Then they have the same throughput. Assume also that they have a large amount of data to send and that no other TCP connections or UDP datagrams traverse this shared link. Also ignore the slow start phase of TCP and assume TCP connections are operating in collision avoidance mode using additive increase, multiplicative decrease at all times. Figure 3.56 plots the throughput realized by the two TCP connections. If TCP is to share the link bandwidth equally between the two connections, then the realized throughput should fall along the 45-degree arrow emanating from the origin. Ideally, the sum of the two throughputs should be equal to the capacity. So the goal should be to have the achieved throughputs fall somewhere near the intersection of the bandwidth share line and the full bandwidth utilization line. Suppose that the TCP window sizes are such that at a given point in time, connections 1 and 2 realize throughputs indicated by point A. Because the amount of link bandwidth jointly consumed by the two connections is less than capacity, no loss will occur, and both connections will increase their window by 1 maximum segment size per round trip time as a result of TCP's congestion avoidance algorithm. Then the joint throughput of the two connections proceeds along a 45-degree line, an equal increase for both connections, starting from point A. Eventually, the link bandwidth jointly consumed by the two connections will be greater than capacity, and eventually packet loss will occur. Suppose that connections 1 and 2 experience packet loss when they realize throughputs as indicated by point B. Connections 1 and 2 then decrease their window size by a factor of 2, as we learned in the last lesson. The resulting throughputs realized are thus at point C, halfway along a vector starting at B and ending at the origin. Because the joint bandwidth use is less than capacity at point C, the two connections again increase their bandwidth along a 45-degree line starting from C. Eventually, loss will occur again, for example at point D, and the two connections again will decrease their window sizes by a factor of 2, and so on. You should assume that the bandwidth realized by the two connections eventually fluctuates along the equal bandwidth share line. You should also assume that the two connections will converge to this behavior regardless of where they are on the two-dimensional space. In our idealized scenario, we assumed that only TCP connections traverse the bottleneck link, that the connections have the same round-trip time value, and that only a single TCP connection is associated with a host-destination pair. In practice, these conditions are typically not met, and client-server applications can therefore obtain very unequal portions of link bandwidth. In particular, it's been shown that when multiple connections share a common bottleneck, those sessions with a smaller round-trip time are able to grab the available bandwidth at that link more quickly as it becomes free. That is, open their congestion windows faster, and therefore enjoy higher throughput than those connections with larger round-trip times. We have just now seen how TCP connection control regulates an application's transmission rate via the congestion window mechanism. Many multimedia applications, such as internet phone and video conferencing, do not run over TCP for this very reason. They don't want their transmission rate throttled, even if the network is very congested. Instead, these applications prefer to run over UDP, which does not have built-in congestion control. When running over UDP, applications can pump their audio and video into the network at a constant rate and occasionally lose packets, rather than reduce their rates to fair levels at times of congestion and not lose any packet. From the perspective of TCP, the multimedia applications running over UDP are not being fair. They don't cooperate with the other connections nor adjust their transmission rates appropriately. Because TCP connection control will decrease its transmission rate in the face of increasing congestion, while UDP sources need not, it is possible for UDP sources to crowd out the TCP traffic. An area of research today is therefore the development of congestion control mechanisms for the internet that prevent UDP traffic from bringing the internet's throughput to a grinding halt. But even if we could force UDP traffic to behave fairly, the fairness problem would still not be completely solved. This is because there's nothing to stop TCP-based applications from using multiple parallel connections. For example, web browsers often use multiple parallel TCP connections to transfer the multiple objects within a web page. The exact number of multiple connections is configurable in most browsers. When an application uses multiple parallel connections, it gets a larger fraction of the bandwidth in a congested link. That is not fair. As an example, consider a link of rate R for capacity supporting 9 ongoing client-server applications, with each of the applications using one TCP connection. If a new application comes along and also uses one TCP connection, then each application will get approximately the same transmission rate of capacity divided by 10. But if this new application instead uses 11 parallel TCP connections, then the new application gets an unfair allocation of more than capacity divided by 2. Because web traffic is so pervasive in the internet, multiple parallel connections are not uncommon. We began this unit on the transport layer by studying the services that the transport layer protocol can provide to network applications. At one extreme, the transport layer protocol can be very simple and offers a no-frills service to applications, providing only a multiplexing-demultiplexing function for communicating processes. The Internet's UDP protocol is an example of such a no-frills transport layer protocol. At the other extreme, a transport layer protocol can provide a variety of guarantees to the application, such as data guarantees and bandwidth guarantees. Nevertheless, the services that a transport protocol can provide are often constrained by the service model of the underlying network layer protocol. If the network layer protocol cannot provide delay or bandwidth guarantees to the transport layer segments, then the transport layer protocol cannot provide bandwidth or delay guarantees for the messages sent between the processes. Although we covered reliable data transfer in this module, we should keep in mind that reliable data transfer can be provided by link, network, transport, or application layer protocols. Any of the upper 4 layers of the protocol stack can implement acknowledgments, timers, retransmissions, and sequence numbers, and provide reliable data transfer to the layer above. In fact, over the years, engineers and computer scientists have independently designed and implemented link, window, transport, and application layer protocols that provide reliable data transfer, although many of these protocols have quietly disappeared. Well, that concludes our discussion of the transport layer. And so we're going to leave the edge of the network and move to the network core. In other words, we're going to start moving to the network layer and examine that link-to-link communication. Well, I know you've got a lot to do. You've certainly got some more assignments to complete in this lesson. So go ahead and take care of that. There will be a module challenge that you have to take. So whatever the schedules are, go ahead and make sure you comply with those schedules as required. See you in Module 4, the network layer.